Hello again, ladies and gentlemen. It's Mr. Donahue working on the 5.7 enthalpies of formation problems. I hope you find this helpful. Audio working, check, everything working. Cool. Awesome. So we're going to start with problem number 29, for which one of the following reactions is the delta H naught reaction equal to the heat of formation of the product. All right, well, we got to know what we're talking about with heat of formation. And the heat of formation is, we're talking about 1 mole of some compound coming from its elements. At standard conditions. So that's STP. So we know we're looking for 1 mole of product, so we can get rid of choice A because we're making 2 moles there. And nothing else, we can't eliminate any other choices because of that. But we can eliminate some other things because we want it at standard conditions, right? So at STP, well, we know that H isn't just H, it should be H2, so it can't be choice C. Again, we got a couple of diatomic molecules that aren't diatomic, so we get rid of D as well as E. So hopefully it's B. We look, we got 1/2 N2 plus O2 gives us 1 mole of NO2. N2 is a gas, O2 is a gas, NO2 is a gas at standard conditions. Awesome. That's it. All right, of the following, delta H formation is not 0. So if we could have a compound, that would not be 0, or an element not at standard state. So for example, SC is a metal. So at standard conditions, almost all metals are solids. Right? We got mercury is a liquid, bromine's a liquid. The only thing that's not in its standard condition here is choice A. Silicon is a solid at standard condition. Phosphate is a solid as well. Bromine is a liquid under standard conditions, and calcium is a solid. So all those things are elements at their standard conditions. So they should be 0. All right, so here we're starting to get into the math, right? So the table over here is the heat of formation, so it's telling you how many kilojoules per mole are given off when you make these substances from their elements at standard condition. We can use them to figure out the heat of the overall reaction, the change in heat. So we go, this is what we do. We got 4NH3, so I got 4 times, well, how much heat is used or given off when I make NH3 gas. So there it is. So I got 4 moles of those, so I got to do 4 times -46. And what about oxygen? Well, it's not on there, right? What are we going to do? Why is it not on there? Because it's an element. At standard conditions, it's 0. So no delta H formation there. Now we look at the products. Again, we got 4NO, so it's 4 times NO, 90, plus 6 for the 6H2O, and we will look up the heat for the H2O. It's -286, right? So now I'm going to combine these numbers to figure out what the overall change was. So for that one, we get -184 kilojoules. Goes to, sum those up, -1356 kilojoules. So looking at this, it should jump out at you that we lost a lot of heat, right? We went from -184 down to -1356. So we got to figure out, well, what's the change? The change, you just do the final minus the minus the initial minus a -184, which is really adding a 184, and it should give you the answer of A. All right, 32. Turn the page. 32 is same thing but different, right? Different problem, but same kind of process. So they give us a chart of knowns, and they give us an overall reaction. So we're going to have to use the heat of formations for those things to figure it out. So I look up C2H5OH is -277.7. Oxygen is 0. And it becomes CH3CO2H. So -484.5, and H2O, which is a -285.8. So figure out what is the overall heat for the reactants, add those together, and it's still just negative 277.7. And it becomes, combine those numbers, and you get negative 770.3. So you go, all right, well, what's the overall change? So you do negative 770.3 minus the negative 277.7, and you get the answer, which is D, as in delta, or something close to it, I hope. Did I do something wrong? No, that's what you get, right? I sure hope so, because that's what I'm saying. So I got circled. I'm having a mini panic attack. All right, cool. And 33, same thing but different. So I'm gonna look to this chart to figure out which heats I'm using. I'm gonna pay attention to the coefficients, so I know if I gotta multiply. So we got 3 NO2, so it's 3 times what NO2 was, which is 34. I'm gonna combine it with a negative 286, and it ends up, the products, we got 2 times negative 207, and NO, which is 90. So I combine them to figure out my heat of reactants. I combine these to figure out the heat of my products. And I get a negative 184. Goes through the reaction to give you a negative 324. So, well, how much did that change? You just take the difference between them, and I get my final answer of C. All right, cool. One more problem. Hope these are helping you. So, again, they give us a table. If they didn't give you a table, it would be in Appendix C. You can look it up in your book or in your SUPA tables that I gave you guys. There's a chart for all these heat formations on Appendix C. So IF5, this one's kind of all coefficients of 1, so I don't got to multiply anything. F2, which is 0, so plus 0, right? Arrow, IF7, which is negative 941. So I got to take the difference there. All right, well, products minus reactants, and I get the answer of, well, wait a minute. All right, cool. Of E. Sorry for that, I was looking at the wrong problem. And those are the 5.7 problems. Hope you found it useful. Hope you learned something. Hope with a little practice, you're experts. I will catch you on the flip side.